Welcome to a new lesson of the VTskills course. Today we are going to talk about water management. Water is one of the most important resources in agriculture, and its management can be critical in the climate change context. Here we can see all the topic we are going to talk about during this lesson. So let's dive in the water management principles. Introduction and context of the water management. It is important to understand the dynamics of water in soil, environment, and plants. The importance of water in viticulture, efficiency in times of scarcity. Water is a critical resource in viticulture. Although the vine is a relatively drought-resistant crop, it requires an adequate water supply at certain times of its cycle. Efficient water management has a direct impact on yield, affecting the number and size of grapes. Quality, affecting the concentration of sugars, acidity, aromas, and tannins. Plant health, excess or deficiency can promote disease or stress. Let's take a look to the Europeans' water context. 40% of the water consumed in Europe is used for agricultural purpose. In Southern Europe, irrigation accounts for up to 80% of total water use. Climate change and projections for 2030 show an increase in water stress, especially in Mediterranean areas. Considering this context, policy frameworks such as the Water Framework Directive, WFD, and the post-2020 CAP are focusing on water management and use by creating laws and instructions on reducing excessive water use and encouraging high-efficiency practices. Climate change and water stress risks to vineyard sustainability. European viticulture is facing a scenario of increasing climatic vulnerability. Projections for the coming decades indicate a combination of factors that will affect both vine production and wine quality. The main impacts can be summarized as follows: reduction of available water in soil and aquifers, increased evapotranspiration due to high temperatures, increased frequency of extreme events, heat waves, droughts, storms, phenological changes in vines, particularly early budding and ripening, shortening of the cycle. Climate change is real and will affect our lives in the future. It is affecting our life today, as more than enough scientific evidence has addressed. Water stress will increase significantly in Southern Europe by 2030, especially in key wine-growing areas. The regions of Andalusia, Tuscany, Alentejo, and Peloponnese are particularly vulnerable. The water balance will be more negative even in years with normal average rainfall due to increased evaporative demand. What will be the implications for the sector? The winemakers and farmers will need to apply adaptation strategies. Long-term strategies like water stress-resistant varieties can be used, as well as short and medium-term strategies like conservation practices and water planning. Technology can help us in water management and in addressing timely water stress, so farmers must know the importance of combining technical knowledge and climate data for smart irrigation management. European regulatory framework towards more sustainable water management. Conscious of the climate change challenges, in particular related to such fundamental resources, and the decline of water quality, in 2015, 9% of groundwater was in poor, unhealthy status, the European agricultural water legislation has evolved from a focus on availability to a model based on efficiency and environmental sustainability. Some relevant regulations can be found in the Water Framework Directive, WFD, 2060 EC, which has the objective to achieve good status of all water bodies by 2027. It regulates abstractions, discharges, and aquifer protection measures. Common Agricultural Policy, CAP, 2023 to 2027 introduced eco-regimes and supported sustainable practices. In particular, it supports water-saving and water reuse infrastructures, and it finances projects if water availability and efficiency are guaranteed. Regulation EU 2020/741 on reused water is fundamental to recycling and reusing wastewater, establishing minimum quality and management requirements for agricultural use. Thanks to water recycling and reusing, that will be addressed in the next topic, it is possible to potentially savings of up to 50% of wastewater. All of these regulatory frameworks reinforce the need to plan and rationalize water use in agriculture, especially in strategic crops such as vineyards. Current technical challenges for efficient water management in viticulture. The transition to climate change-adapted viticulture involves facing several technical challenges related to irrigation planning, implementation, and monitoring. First, as already mentioned, we must consider climate variability and uncertainty. In particular, water will be less available due to more erratic in-season rainfall. But also, extreme events, storms, or intense droughts will create damage to the plants and will make seasonal water management planning difficult. Another problem can be found in the lack of a specific calculation of water needs. Many vineyards do not have local evapotranspiration studies or plot water balances that are fundamental to correctly estimating the water needs for the plants. Also, considering what we said about climate change and the difference in rain distribution, water planning based on previous experience alone becomes insufficient. The farmers need more information and insights on the water availability and dynamics during the vegetative and productive cycle of the plants. Inefficient or poorly adapted infrastructure can result in a bigger problem than you may think, as the lack of efficiency means waste, water losses, and failure to meet irrigation targets. Some examples of inefficiency are gravity or sprinkler irrigation systems are still used in unsuitable areas, or the lack of pressure or homogeneous distribution in drip irrigation. Last but not least, the absence of control and monitoring tools can cause poor implementation of moisture sensors, flow meters, or weather stations. This can be due to a low level of integration of digital technologies to program or adjust irrigation based on data. Overcoming these challenges requires technical training, investment in infrastructure, and the increasing use of technological tools that enable intelligent water resource management in the vineyard. Let's take a look at the basic technical knowledge that we need in water management. The water cycle in the vineyard, key processes and their influence on irrigation management. Understanding the water cycle in the soil-plant atmosphere system is fundamental to planning and implementing an efficient irrigation strategy. Some elements must be considered, namely the infiltration, the retention, the natural loss, the transpiration, and the evapotranspiration. Infiltration is the capability of water to enter the soil pores. So, it depends on soil structure and texture. In general, we can say that in sandy soils we have fast water infiltration, but less retention. Instead, in clay soils, we have slow infiltration and higher retention, but we also have a risk of waterlogging. Retention and availability are the capacities of the soil to retain water within its hollow spaces, making it available for the plant to absorb the water. The useful water for the plant is the water contained between the field capacity and the wilting point. We will talk about this in the next slide. The natural losses are that portion of water not available for the plant because it returns to the environment in the form of water vapor or by reaching such depths in the soil that the plant's roots are not capable of reaching it. So we can find natural losses for evaporation and percolation. Another natural phenomenon in water dynamics is the transpiration, which is a physiological process by which the vine loses water by exchanging gases. It increases with high temperatures, low humidity, and high solar radiation. Merging all those elements together, and you will have more or less the evapotranspiration, etc., one of the most important indices to address the plant's potential water state. It is the sum of evaporation and transpiration, and it represents the total water demand of the crop and varies according to climate and phenology. So, as the objective of water management is to replenish with irrigation only the water actually consumed by the crop, avoiding unnecessary losses, all the previous values are of fundamental importance to address the plant's actual water need. Technical calculation of water needs in vineyard, practical methodology. As said in the previous slide, to determine when and how much to irrigate, the concept of crop evapotranspiration, etc., is used. The basic formula of evapotranspiration is etc. in mm=sign Ito x Kc, where Ito, or reference evapotranspiration, represents the amount of water that would be lost by a reference crop, usually short, well-irrigated grass. Kc, or crop coefficient, adjusts Ito to the specific characteristics of the vineyard and varies throughout the growing season. Here are some practical examples of Kc in vineyards according to growth phase. We can have, during sprouting, a Kc of approximately 0.2-0.3, during the vegetative development. The Kc can be of 0.4-0.6, and during veraison of 0.7-0.8. As you can see, the maximum value of the crop coefficient can be found during the veraison, where we have the peak of temperature and water needs. Last but not least, during maturation, the Kc is circa 0.305. Additional factors to consider when computing the ETR are soil type. Sandy soils retain less water than clay soils. Root depth, greater in old vines or vigorous rootstock. Ground cover. Mulching or ground covers can reduce evaporation and modify the effective KC. Important! The calculation should be updated weekly or fortnightly according to the climatology and the state of the vineyard using local weather stations or agroclimatic services. The role of soil in water availability for vines. Soil structure and texture are fundamental factors in the dynamics of water available to plants. First of all, let's consider the soil texture. That is the mean dimension of soil particles and the level of porosity, hollow parts in soil volume. We have sandy soils with large particles and high porosity. They infiltrate water quickly but retain little for short periods of time. These soils requires frequent and low doses of water distributed to assure the plants to have the right amount of water available. Loamy soils are between sandy and clay soils. Usually, they have good storage potential and good water availability for a much prolonged period of time compared to sandy soils. Still, they can be affected in short measures by waterlogging. Clay soils have fine particles with high cohesion. Those soils can retain a large amount of water, but some of it is not available to plants due to their strong capillary tension. In this case as well, it is possible to observe waterlogging phenomena after heavy rains. Considering soil structure and the dynamics of water in soil, we can find some key hydrological concepts. Field capacity, FC, percentage of water remaining in the soil after gravitational drainage, is the condition ideal for the plants. Permanent wilting point, PWP, moisture level at which the plant can no longer absorb sufficient water and wilts irreversibly. Useful water, the water actually available to the crop, comprised between the FC and the PWP. Each of the previous hydrology concepts does not always manifest itself in the same way. For each soil type, the water levels at which we have field capacity or the permanent wilting point change. To make the concept clearer, let us see some examples of available water according to soil type. Depending on the type of soil and the useful water, or percent volume, we have sandy soils with 5 to 10% usable water, loamy soils with 15 to 25% usable water, clay soils with 20 to 30% usable water. It is important to know the soil texture and structure in order to design adjusted irrigation schedules, optimizing water use efficiency, and reducing losses through runoff or percolation. Now that we know the dynamics of water between plants, soils, and environment, let's take a closer look to the agronomic choices that we have for water conservation. Mulching in viticulture, moisture conservation, and soil improvement. What is mulching? Mulching consists of covering the soil around the plant with organic or synthetic materials to conserve moisture, improve the physical and biological conditions of the soil, and reduce water losses. Some key benefits can be found in using this technique. Evaporation reduction. Mulching can reduce the loss of surface water. Improved infiltration by facilitating the penetration of rain or irrigation water into the root profile. Weed control mulching can help reducing competition for water and nutrients. Thermal protection by moderating the temperature fluctuations in the root zone. Supply of organic matter that can improve the soil structure and fertility. We have different types of mulching that can be used, in particular are possible, or organic mulching by using straw, dry leaves, shredded pruning waste, compost, or inorganic mulching relying on biodegradable plastics, polypropylene geotextiles. Let's consider some practical elements. In rain-fed viticulture or in areas with dry summers, mulching can reduce irrigation needs by up to 30%, so it can really help water management and water accumulation in the soil. To be sure that the mulching is correctly performed, it is important to select materials that do not interfere with soil aeration. For this reason, but also for the organic matter, so supplying in the soil and for economic sustainability, it is best to prefer organic mulching to inorganic one. Nonetheless, annual or biannual renewal of coverage is recommended on organic materials to maintain efficacy. Vineyard canopies, a multifunctional strategy for water conservation. What are ground covers or cover crops? They are living plants growing between the rows of vines or over the entire vineyard surface, used to protect the soil and optimize water and nutrient management. Some key benefits can be found like water conservation. The cover crops can reduce direct evaporation of water from the soil, can improve infiltration by breaking surface compaction, and can reduce runoff and erosion. Also, they provide for the improvement of soil structure and fertility by increasing organic matter and promoting microbial activity. Fundamental for the environmental sustainability is also the increased functional biodiversity of this practice, as the cover crops can favor pollinators and natural enemies of pests and improve the resilience of the vineyard ecosystem. Let's take a look at the types of green covers. There are mainly two kinds, the natural or spontaneous and the sown or artificial. These spontaneous are autochthonous species that colonize the vineyard. They are important for biodiversity, and they can provide us with some indirect information on soil characteristics and state. General directions by observing the roots of grasses can be provided. For example, taproots can be found in very compact soil. Instead, clumps of fine roots are typical of very aerated soils. The sown cover crops are sownings of grasses, fescue, oats, or legumes, clover, vetch, for specific functions: nitrogen fixation, weed control, water conservation. They can be chosen based on the objective we want to reach and can be seeded just where needed. Some practical considerations to take into account. Proper management, pruning, mowing is fundamental to avoid excessive competition for water during critical phases of the vine, flowering, veraison. In arid areas or in dry years, inactive summer covers or alternate strip management can be chosen. Ground covers are an essential tool for improving vineyard sustainability, helping to meet the challenges of climate change. Soil modeling in viticulture, techniques for water and soil conservation. We can also manage water dynamics by working on the soil. Considering the correct planting layout based on slopes and the depth of groundwater can be strategic in the long-term period for water management. Land management using specific techniques can help to reduce surface runoff, increase water infiltration in the root profile, and prevent water erosion. Let's see some practical examples. First, planting on contour lines. Contour consists of the arrangement of rows of vines following lines of equal altitude. It can help decrease surface water runoff and erosion problems. It can also help increase the retention time of the water in the ground. In some cases, the slope is so high that we need benches or terraces. Those are the construction of flat platforms on steep slopes that break the slope into short sections, reducing runoff and favoring soil and water retention. They require significant initial investment, but are essential in mountain viticulture. To properly manage water runoff, the infiltration trenches, swales, are fundamental. Those are shallow and wide channels dug following the contour lines. They capture rainwater and allow it to gradually infiltrate into the ground. They can be combined with ground covers or trees to improve water harvesting and water use. As always, some practical considerations. These techniques should be planned taking into account soil type, slope, and local rainfall. They require maintenance to ensure their optimal functioning and to avoid clogging or localized erosion. Overall, land modeling is a very effective passive strategy to conserve water in the vineyard in a sustainable way, especially in semi-arid or mountainous areas. When needed, irrigation can help saving our vineyards, plants, future and present production. But correct irrigation is not an easy task, and a great deal of consideration and analysis must be taken into account. Drip irrigation system in viticulture, optimizing water and vineyard yields. Drip irrigation is the most widely used and recommended localized irrigation technique in precision viticulture. How does it work? Water is delivered in individual drops or small flows through emitters placed close to the plant. The application is slow and steady, allowing efficient absorption by the root system. Why use drip irrigation? We can have some technical advantages. Precision, so the possibility to adjust exact doses according to the phenological stage of the vine and climatic conditions. Efficiency by reducing evaporation losses compared to sprinkler or blanket irrigation. Improved vineyard health, reaching lower humidity and reducing the risk of fungal diseases. Flexibility as it is compatible with fertigation systems, injection of nutrients dissolved in water. But the most important thing is water saving. By using drip irrigation, it is possible to reduce water consumption by 40 to 60% compared to traditional methods. Greater uniformity of application, which is essential to achieve homogeneous ripening of the grapes, can be achieved through this system. Some practical considerations to take into account. Drip irrigation requires proper technical design. Controlled working pressure and water filtering to avoid clogging are just some examples. This irrigation requires regular maintenance, dripper cleaning, flow rate checks that can be time-consuming. Well-managed drip irrigation is a key tool to increase water sustainability and improve wine quality in resource-scarce contexts. Controlled deficit irrigation in vineyards, a strategy to improve quality and water efficiency. Controlled deficit irrigation, CITI, consists of applying a level of irrigation below the maximum evapotranspiration demand of the crop, but in a planned and strategic manner. The controlled deficit irrigation induces moderate water stress in vegetative growth phases, where the plant can tolerate it without compromising productivity. It improves the concentration of soluble solids, sugars, and phenols color aroma wine structure. Which are the critical phenological stages in the grapevine for RDI? Let's consider that for each phase, there is a recommended level of irrigation. So, from budding to full flowering, we want good water availability for the plant development. From fruit set to veraison, we want to apply controlled deficit irrigation. From veraison to harvest, we want to apply moderate irrigation according to the quality objective. Why use RDI? Some benefits of this technique includes the improvement of the balance between vegetative and reproductive growth, the reduction of irrigation water and energy costs, and increased quality of the harvest, better sugar, acidity, tannins. Also, for RDI, we have some practical considerations. It requires frequent monitoring of soil moisture and plant water status, leaf water potential sensors. If carried out badly, excessive stress that compromises photosynthesis or bunch production should be avoided. RDI is an advanced technique that turns irrigation management into a winemaking improvement tool as well as a water-saving strategy. Rainwater harvesting in the vineyard, efficient use of a natural resource. Rainwater harvesting represents an effective strategy to optimize the use of water resources in viticulture, especially in regions where rainfall is seasonal and irregular. This technique captures the water from impervious surfaces, roofs, compacted roads, terraces, and store it for future use in tanks, basins, or cisterns designed to minimize evaporation. Using rainwater harvesting can provide a viable water resources for the reduction of water stress in times of drought, the reduction of pressure on aquifers or public networks, and the improvement of the overall efficiency of the farm by using a free and renewable resource. We have some elements composing the collection system. In particular, we must have a catchment area, the roofs of agricultural buildings or sheds, a conduction system, gutters, pipes, infiltration trenches, a storage system, tanks, waterproofed basins, cisterns, a filtration system, inlet filters to prevent sediment or contaminants. Practical considerations to take into account. Be sure to size the reservoir according to the catchment area and average annual rainfall. Keep gutters and filters clean to ensure water quality. In organic vineyards, the harvested water can be used directly without chemical treatment. Do you want an example? A catchment on a 500 square meters roof with 400 millimeters annual precipitation can have a catchment potential of circa 160 cubic meters of water per year. Nice! Aided storage infrastructures in vineyards, ponds, and reservoirs. Why are they important? Irrigation ponds and reservoirs allow wine growers to ensure water availability in times of high demand or shortage, reducing dependence on external sources and increasing the resilience of the farming system. We have two main types of pond and reservoir used in agriculture, the irrigation ponds and the above-ground or underground tanks. The irrigation ponds are large areas excavated in the ground and coated with waterproof sheets, PVC, HDPE, to prevent infiltration. They are designed to capture runoff, rainwater, or store pumped water. They can store a large amount of water, but there are regulatory constraints on their use. Consider also that those large ponds have a much higher surface exposed to the atmosphere, and consequently, water can evaporate at high rates. Instead, the above-ground or underground tanks are collection systems made of polyethylene, vitrified steel, or fiberglass and are usually smaller in volumes. Even if they can store less water compared to the ponds, the evaporation rate is lower. It is usually used as an accumulator for localized irrigation or fertigation. Let's consider the design and management aspects. It is fundamental to calculate storage capacity according to vineyard area, water requirements, and rainfall. As those systems can be expensive, we don't want to create something that is not functional. If we store less water than we need or too much, we don't reach the right efficiency. We must provide overflow systems to prevent damage due to excess water. Pumps and an overflow system can help in the task. We must maintain sheets or structures in good condition to avoid evaporation or infiltration losses. Depending on the material, the plastic sheets can last from 5 to 10 years. But we must consider alternative materials to plastics, as the formation of microplastics is now a big issue, as they can pollute the environment and the water supply. Here, a practical example. A 1,000 cubic meter, 10 by 10 by 10 meters, or 50 by 10 by 2 meters, etc. Pond can cover the backup irrigation of a 5-hectare vineyard for 2 weeks in summer in semi-arid areas. Implementing smart irrigation systems in viticulture, optimization, and sustainability. What is a smart irrigation system? It is a set of technologies that allows irrigation to be managed in an automated and adaptive way, using real soil, climate, and plant data to decide when and how much to irrigate. To use smart irrigation, we need sensors that provide us with the correct information. For example, we can have a weather stations composed by multiple elements. We will see this more in Department in Topic 4, 2.3. The main elements that can give us the right information and data are soil moisture sensors. Those sensors can detect the volumetric water content in the root profile. They are of different types based on how they work. Tensiometers, capacitive, and FDR, frequency domain reflectometry, are the most present and used. They provide alerts or trigger irrigation automatically when the moisture level drops below a critical threshold, and if connected with the irrigation system, can irrigate automatically when needed. Local weather stations. They measure essential climate parameters: temperature, relative humidity, wind speed, solar radiation, and precipitation. They are useful as they can provide us with information on the atmospheric conditions with multiple data sources and not just one like in the previous case. For this reason, they calculate ETO to adjust water requirements according to climate. Automatic controllers and digital platforms are programs that monitor and manage irrigation remotely. They integrate weather forecasts to avoid irrigation prior or right after a rainfall. They use historical analysis to improve decision-making. Why use those solutions? Because they have technical and economic benefits, like allowing water savings of 20% to 40%, can reduce energy costs associated with pumping and distribution, can improve fertigation efficiency, less nutrient leaching, and increase grape quality through precise control of the plant's water status. Let's consider some implementation issues. First, we can have a moderate initial investment that pays for itself in 4 years, and we need for basic training in data interpretation to ensure the efficiency of the system. Smart irrigation represents the future of water management in viticulture, aligning quality production and environmental sustainability. Fertigation in viticulture, key technique for efficient nutrition and irrigation. Fertigation is the application of mineral nutrients dissolved in irrigation water, allowing their direct delivery to the root system of the vine, synchronized with its physiological demand. It allows us to optimize fertilizer use, as the nutrients are delivered directly to where and when the plant needs them. It can improve water saving because the volume of irrigation required is reduced by combining water and nutrients. It can help increasing nutritional efficiency as better nutrient uptake compared to broadcast or spray applications. And lastly, it allows us to reduce environmental impacts, in particular by reducing leaching of nitrates and other pollutants into aquifers. The essential elements of a fertigation system are the injectors or metering pumps that introduce fertilizers into the irrigation network, the protective filters that prevent clogging of the drippers, and the automatic controllers, which allow the fertilizer concentration in the water to be adjusted according to the needs of the crop. How can we manage fertigation in the vineyard? We must plan this operation considering the phenological state of the plant and the in-season moment. So, during sprouting vegetative development, vines have an increased need for nitrogen. During flowering and fruit set, we need to balance the demand for phosphorus and potassium. In the veraison ripening moment, we have to increase of potassium to improve fruit quality. Some practical considerations: we need to regularly monitor water quality, pH, and conductivity to avoid precipitates. It is correct and recommended to adjust fertigation programs to climatic conditions and vineyard load. Fertigation, integrated with an efficient drip irrigation system, is a fundamental tool for improving the profitability, sustainability, and enological quality of the vineyard. Now, let's talk about vineyard design, planning, and adaptation for water optimization. Irrigation planning in vineyards, adjusting water to the phenological cycle and climate. Proper irrigation management involves knowing in detail when and how much to irrigate with the objectives of water use optimization or enological quality improvement and losses avoiding due to excess or deficit of water. There are some key vine stages and irrigation recommendations. In particular, each phenological phase has a water requirement. In this respect, there are several irrigation strategies. 1. During sprouting, vines have low water needs. The strategy is moderate irrigation if necessary. 2. During flowering, we will have high water needs to ensure adequate water availability. 3. In fruit, there is usually a high need for irrigation to guarantee the number of berries. 4. In berry development, the need is medium-high, so we need to keep humidity under control. 5. During the veraison, the need is medium. If needed, we will apply a moderate deficit irrigation to concentrate sugars. 6. In ripening, the necessity is low, so we will apply minimal or controlled irrigation to maintain quality. The irrigation also need to adapt to climatic conditions, so we need to monitor daily or weekly evapotranspiration, ETO, adjust water inputs according to actual rainfall, and anticipate extreme heat waves to prevent severe stress. We want to suggest some recommended tools that you can use for this purpose: local weather stations, water balance models, and moisture sensors in the soil. Correct irrigation planning ensures that the vine receives adequate water at each stage of its cycle, maximizing the quality potential of the wine and improving the vineyard's resilience to adverse climatic conditions. Adaptation of vineyards to water scarcity, varieties and rootstock selection. In the face of increasing drought conditions, the selection of better adapted varieties and rootstocks makes it possible to reduce the water demand of the vineyard, maintain acceptable economic returns, and preserve or improve the oenological quality of the grapes. We have multiples cultivar that can be selection due to their drought-tolerant capacity. Most of them are typical of European areas that are arid, like the Grenache in Spain and France. In Italy, it is known as Cannonau, which is drought-tolerant, has late ripening, and good quality in arid areas. We also have the Monastrell, Mourvedre, with high resistance to water stress, as it is suitable for hot and dry climates. Another example can be the Tempranillo, adaptable, especially when managed under deficit irrigation strategies. But as the vine is composed also by the rootstocks, we can also choose a rootstock variety that is drought-tolerant. In particular, we have the 110R, Richter 110, characterized by medium-high vigor, excellent drought resistance, and deep rooting. The 140 Rue, Rougerie 140, with tolerance to drought and poor soils and high vigor, and the 1103P, Paulson 1103, that is very drought-tolerant and is used on dry limestone soils. Some selection considerations we must look after: first, the compatibility with the grafted variety, then the adaptation to soil characteristics, texture, salinity, and lastly, the combination of drought tolerance with soil disease resistance, if possible. What are the impacts on water management? We can reach a reduction in the frequency of irrigation required, an increased efficiency in extracting water from deep soil layers, and an improved physiological response to periods of prolonged water stress. Integrating water resilience criteria into new plantings or restructuring is an essential proactive measure for the future sustainability of the vineyard. Efficient management of rain-fed vineyards, strategies for adaptation and resilience. In rain-fed viticulture systems, where no artificial irrigation is applied, proper water management depends on specific agronomic practices that maximize the use of natural soil moisture. We can describe 4 main strategies, some of which we already discussed during this lesson. Selection of adapted plant material, grape varieties with tolerance to water stress, Garnacha, Monastrell, Tempranillo, and rootstocks with deep roots and efficient water extraction, 110R, 140 Aru. Soil management, natural mulching, like the use of prunings or cover crops to protect the soil. Minimum tillage to avoid deep plowing and preserve soil structure and soil retention capacity, and controlled vegetation cover with the use of spontaneous or sown cover crops managed by mowing to reduce evaporation without over-competition. Vineyard design, low planting densities, 2,000, 3,000 plants ha, to reduce root competition, and orientation of the rows to maximize water uptake and soil shading. Vigor control, pruning adapted to balance leaf mass with limited water availability, and load regulation by cluster thinning if necessary. What results can we expect? For example, we can have an increased efficiency in the use of available rainwater, a better adaptation of the vineyard to prolonged drought events, and the preservation of grape quality under extreme conditions. Well-managed rain-fed viticulture not only allows cultivation in arid regions, but can also produce wines of high expression and territorial typicity. And now let's talk about drainage and water harvesting. Vineyard drainage management, key to soil health and water efficiency. Why is drainage important? Poorly drained soil can lead to root anoxia, lack of oxygen to the roots, an increase in fungal diseases, phytophthora, armillaria, and reduced vigor and plant mortality in severe cases. Waterlogging can be deleterious to the vineyard, and we can have too much water. We can identify multiple drainage management strategies. Vineyard design. Plan planting in areas with slight slopes, 2 to 5%, and avoid planting in low-lying areas without proper natural water outlets. Implementation of drainage systems, surface drainage by means of ditches, channels, or swales that guide excess water away from the plots. Underground drainage is achieved by the installation of perforated pipes at controlled depths to collect excess water and channel it to evacuation points. Soil management. Avoid compaction caused by heavy machinery, especially in wet weather, and maintain a porous structure through controlled tillage, organic matter inputs, and well-managed ground cover. Some positive consequences of good drainage can be identified as improved aeration and root development, reduction of losses due to water-related diseases, improved efficiency of irrigation applied, reduction of vine stress in situations of heavy rainfall, and proper design and maintenance of the drainage system ensures that available water is a resource and not a problem for the vineyard. Passive water harvesting in vineyards, infiltration ditches, swales, and natural techniques. Infiltration trenches, swales, are shallow channels dug following the contour lines of the plot, which main purpose is to detain, store, and infiltrate rainwater that would otherwise be lost to surface runoff. Those trenches capture rainwater running down the slope, storing it temporarily, allowing it to infiltrate slowly into the soil profile. They prevent agricultural soil erosion and can improve the recharge of water available to plants. The basic design of the trenches comprises a depth of 20 to 50 centimeters, depending on rainfall and soil characteristics, and a width proportional to the slope and catchment volume. It is best to have perennial vegetation or plant cover inside to reinforce infiltration and stabilize the walls. We have other complementary techniques to terraces as micro-infiltration basins, which are small individual depressions between rows, vegetated berms, which are gentle ridges that slow the flow of water on long slopes, and controlled runoff collectors that are channeling systems to recharge areas. The advantages of infiltration trenches are multiple. First, an increases soil moisture without additional irrigation. The improvement of soil structure and biodiversity, and the reduction of erosion damage in heavy rainfall events. Some implementation considerations. Trenches require a design adapted to each terrain and need periodic maintenance to remove accumulated sediments. Incorporating infiltration trenches into vineyard design helps to naturally address the challenge of climate change and water scarcity. Vineyard terraces and terraces, ancient tools for sustainable water and soil management. Agricultural terraces are artificially leveled land surfaces arranged in a staggered pattern along slopes to efficiently cultivate crops and manage water resources. The main functions in the vineyard include the reduction of the effective slope and the reduction of the surface runoff speed of rainwater. Improved infiltration, as water remains longer in the surface profile, favors its absorption by the soil. Soil conservation thanks to wind and water erosion prevention, in particular of the fertile horizon. Facilitation of agricultural management, as they enable access to light or medium-heavy machinery. Some design features to consider. The platform width must be adapted to the machinery or planting density. Reinforce slopes by using vegetation or dry stone walls to prevent landslides. Create drainage channels to evacuate excess water in very heavy rainfall events. We have multiple types of terraces, in particular the absorption terraces, designed to capture and infiltrate water, semi-arid areas, and the evacuation terraces, designed to quickly evacuate excess water, very rainy areas. The terraced vineyards in the Douro Valley, Portugal, La Azarquia, Malaga, Spain, Ribera Sacra, Galicia, Spain, Moles, Valtellina, Lombardy, Italy, Candia and Colli dell'Uni, Tuscany and Liguria, Italy, and Rhone Valley, France, are some of the most famous examples of terraced vineyards. Those are some spectacular examples of human landscaping, and some of them, Lavaux, Switzerland, are part of UNESCO World Heritage. So, one additional benefit is the conservation of the rural landscape and agricultural cultural heritage, but also increasing the ecological value of the vineyard species habitats. Some practical considerations. Terraces have a high initial investment, but with long-term payback and a need for regular maintenance, repairs to walls, slopes, channels. The use of terraces in terraces makes it possible to combine high-quality wine production with the preservation of natural resources and the landscape. Integrated water management in vineyards, combining techniques for maximum efficiency. Water use efficiency in viticulture does not depend on a single practice, but on the coherent integration of multiple strategies adapted to the specific conditions of each estate. We have some main components of a combined strategy. High-efficiency irrigation system by using drip irrigation, controlled deficit irrigation, RDI according to phenological phases, and automation and use of humidity and climate sensors. Conservation of soil moisture by applying organic mulching or biodegradable plastic, implementing permanent or seasonal vegetation covers, and applying minimal tillage practices to maintain soil structure. Rainwater harvesting and storage with systems like water harvesting on agricultural roofs and impermeable surfaces, and construction of reservoirs and tanks sized to meet water demand. Adapted genetic selection using drought-resistant varieties and rootstocks, and lowering the density of plantation design in semi-arid areas. The benefits of the combined strategy can be found in the reduction of water consumption by 30% to 60% under normal conditions, the increased resilience to extreme events, droughts, heat waves, the improved enological quality through more precise water control, and the reduced operating costs, less energy, fewer inputs. At least some final considerations. Each vineyard must adapt its combined strategy considering local climate, soil type, variety grown, and availability of resources. Integrating various techniques of water conservation, harvesting, and efficient use of water is the way towards a more sustainable, profitable, and climate change-adapted viticulture. We now present a remarkable example of sustainable vineyard management in organic farming located in Tuscany, Potere Licenziol, one of the founders of the Biodistretto del Chianti Association. The approach of the owners, Valeria and Luca, is deeply rooted in collaboration, innovation, and respect for the surrounding environment. By establishing strong relationships with local institutions, technicians, and neighboring producers, they have managed to create a network that supports both environmental sustainability and economic resilience, knowledge, and enthusiasm, leading to continuous implementation of practices in organic farming. The following slides aim at presenting the water management practices carried out at Licenziol by the careful management of permanent cover crops. As seen before, a key factor to be considered for soil management is the presence or absence of a vegetation cover, which can be managed in order to positively influence soil functionality and water balance. At Licenziol, soil water management is conducted primarily by the accurate management of permanent cover crops. In a vineyard with permanent cover crops, the rapid and deep expansion of grass roots increases water infiltration capacity and enhances water retention, due to the higher organic matter content in the soil. The competition with the grass also reduces vine vigor, limiting the vineyard overall water and nutrient consumption, as well as encouraging deeper root development, improving the plant absorption capacity. The ground cover acts as a biochemical activator between the soil and living microorganisms and regulates the availability and absorption of nutrients. The grass stimulates microbiological activity, which transforms organic molecules in mineral substances. The presence of well-established ground cover helps to maintain optimal soil porosity throughout the growing season, thereby facilitating an effective root system activity and development. Proper management of mowing residues creates a dry surface mulch that effectively reduces losses due to surface evapotranspiration. As the season progresses, grass growth gradually declines and eventually ceases during the dry summer period. Mowing at this stage contributes significantly to improve water management in the vineyard by creating a dry mulch that helps to retain soil moisture, optimizing the vineyard's water holding capacity and reducing the need for irrigation. After the rainfall events of late summer near harvest time, grass growth resumes. However, during ripening, the presence of the competition of the cover crop contrasts the resprouting of the canopy and the swelling of the berries. To achieve effective mulching, the study case estate employs a chain rotary cutter, which is particularly suitable for managing dense or coarse vegetation. Unlike traditional hammer flail shredders, the chain flail mechanism mows the grass, creating a more uniform and persistent mulch layer. This method enhances soil moisture retention, suppresses weed regrowth, and facilitates the gradual release of organic matter into the soil, contributing to improved soil structure and fertility over time. Moreover, this type of shredder is lighter in weight compared to traditional models, reducing the risk of soil compaction, which is crucial to preserve a high soil quality, particularly when working on moisture-sensitive soils or during periods of higher humidity. Minimizing compaction helps to preserve soil structure, to maintain adequate aeration and drainage, and to support the activity of beneficial soil microorganisms, all of which are crucial for long-term vineyard health and productivity. As we wrap up this lesson on water management, let's first take a moment to review the key points and the main references. Final summary: key principles for efficient water management in viticulture. Throughout the module, we have learned that water is a critical resource in wine production, directly related to the quality, productivity, and sustainability of the vineyard. Climate change increases the risks of water stress, prolonged droughts, and extreme events, making the adoption of efficient water management practices urgent. Main strategies learned: use of efficient irrigation systems such as drip and controlled deficit irrigation, CIDI. Implementation of agronomic practices to conserve water in the soil, mulching, ground cover, contour planting, infiltration ditches. Rainwater harvesting and storage through appropriate infrastructures, ponds, reservoirs. Selection of drought-resistant varieties and rootstocks as a genetic adaptation strategy. The combination of strategies and their specific adaptation to each vineyard is the key to maximizing water efficiency and ensuring the sustainability of wine-growing operations. Innovation, continuous training, and strategic planning are essential to face the future challenges of viticulture in the face of water scarcity. In short, efficient water management not only protects a vital resource, but also ensures the quality, profitability, and future of viticulture. Here are the references we've used throughout this lesson. Thanks for following along. We hope it's been useful. See you in the next lesson.